Testing the sound. All right. Good morning, everyone. Welcome to our last week of the course. Let me start first by saying that we are really happy that you guys are continue working on the course and that you keep up with the good work, especially with these weird conditions that we have to face nowadays. On that regards, I really hope that you, your family, and your loved ones are safe and staying healthy. Also, I want to mention that I don't think we remind you guys about this, but the university, through I don't know if it is blue or it has changed, but it doesn't matter, is running a course evaluation. And if you guys can take a few minutes to complete that course evaluation, is priceless for us, because it provides us with a lot of information. I know it's going to be a little bit difficult or weird in this case, because we switched to this online mode or solely online mode in the last few weeks. But even though, if you can guys provide us any insights, any comments, any feedback, maybe from the two different parts of the course that we were doing face to face and this online part, it will be truly appreciated. It usually helps us to improve and try to get rid of the things that did not work during the course. So if you can take the time for doing that, we would really appreciate that. What else? As you noticed by Ramsey's email, assignment 9 has been posted. It's about MPI, of course. The office hours, because we shift again the due date, is going to be Wednesday from 2 to 3, and then Friday, I believe, at noon or something like that, or 11, around that time. It's also in Ramsey's email. I am going to try to keep an eye on the chat, so if you guys have any questions, please just post them there. And the plan for today, so what we have done in this last part of the course was to start harvesting and learning the power of parallel computing and improving the performance of our codes. But one thing that we cannot always do without measuring how good or bad our code is improve things. So what we're going to be discussing today in particular is how to do that, and that goes by the name of profiling. So the idea for today is that we are going to discuss what profiling is, the different techniques that we have for actually profile a code, and some tools in particular. Somehow you had been doing something like this when we asked you to do this kind of a scaling analysis, but the profiling is a more, little bit more fine-grained or more resolution on actually measuring what the code is doing. I've seen some questions about, I think, the diffusion time step. I think Ransom is dealing with that. So again, if you have any other questions, please just post it there. We will try to address. So there is a 20-second delay between the video that you are seeing and me speaking. So I'm going to try to make some pauses during the lecture just to catch up with any questions. And similar answers who is in the chat as well. So profiling. So what profiling is a way to measure how the code is performing, like what the program is doing. In particular, there are different ways that we can profile a code. We can analyze the code by taking the metric of the time, like looking at how long it takes a particular function or part of the code to run, or we can actually profile also the uses of memory. So any kind of utilization of resources, of the computational resources that the code does can be measured. So that's the idea of profiling, is having an idea of how certain parts of the codes are using the resources that we have available. Now, the idea, the name of the game here is, okay, we measure the code, we select the metric we want to use, timing, memory utilization, communication can be, we find where the problems are, where the bottlenecks, and then we try to make improvements. So it's a kind of evidence-based method in that regard, similar to debuggers. So if you think about debuggers, we try to match this idea of what we think our code was doing, the mental model that we had about our code, and what the actual code is doing. So we collect evidence and we try to add upon that. So that's the basic idea of why we need to profile and measure things. So one of the most common ways to look at the code and the performance of a code is to look at where the time is being spent. So how the program is spending the time. The idea here is finding and focusing the expensive parts, meaning the parts of the code that are spending most of the time, in this case, and try to not spend too much time optimizing parts of the code that don't matter. So for instance, if you had a code that runs for 1 million iterations, just to put some numbers, and there is an initialization routine, which is run only once at the very beginning of the code, and that initialization routine takes only 1%, 2% of the total time, then definitely it's not worth it spending time looking at how to optimize the initialization if the 98% of the time is being spent somewhere else. It sounds like obvious, but again, it's some of those things that is worth specifying and clarifying since the beginning. So what I have in the screen is a snippet, a piece of code, and it's just to show you one of the techniques that can be used to profile, to measure how the code performs in terms of how much time is spending. So in principle, for profiling, there are two main techniques. One is called thrashing and the other is called sampling. And in addition to that, you may have an implementation or an implementation of the profiling where you had to instrument your code, and another where you don't instrument your code. And we're going to see what I meant with that. So one is instrumenting versus instrumentation free. So instrumenting means that you need to add some new parts of the code, some new sentences, some new instructions in order to be able to measure how the code performs. And the piece of code I'm showing here is, it doesn't matter much what it's doing, it's just solving some differential equations and evolving in time. Is setting some boundary conditions on the beginning. So again, this is part of the initialization. So I'm not going to be concerned about this for the moment. And this is the main loop. And what I want to know is, okay, how much time is being spent in this main loop. So what I have is two routines, a tick and a talk. And basically, whatever goes between these two is measuring time. And there is a pointer to a time variable tt here, which will allow me to access how much time is being spent during that for loop. So this is an example of tracing, because actually I'm just looking at the whole evolution of the whole run of the code, and also of instrumenting the code, where I'm adding two specific instructions, a tick and a talk, to actually measure how much time this piece of the code is taking. Okay? Any questions so far? I'm going to pause for a few seconds just to see if there are any questions in the chat. Okay. In addition to this, there are a couple of utilities that some of you may have been using already, and these are from the operating system mostly. So we have the time command. I think some of you used it for the last assignment. Then we have top PS, which shows the processes running in your computer. This one I have suggested to some of you because I found it to be very interesting. HTOP is very similar to top in the sense that it allows you to see the processes running and also the utilization. But then I have an example here. Let me just quickly show you. So this is HTOP running on my laptop right now. And the interesting thing of HTOP is that also shows you, so in this case this laptop has only 4 CPUs, but also shows you the utilization per CPU, so it shows you the utilization in memory. You can see this machine is exhausted in the memory pool, and it's also showing that it's doing some swapping. So that is when you run out of memory, and then the operating system starts to use part of the hard drive as an extension to memory, so the application can still run. So it's nice. It gives you a little bit more of interface information when running HTOP, but similar to top, allow you to control and see the performance of the different processes running. In addition to that, there are other tools more related to, for instance, communication through the network. Like if you have an application where most of the things are being done by communicating, then you may want to see of any of these commands. But these are all commands that are mostly available in Linux type operating systems, and so it's a good idea to keep them in mind and take a look whenever you have the chance to. So the operating system can also aid in tracing, in looking at the performance of your applications and measuring these metrics as well. So let's take a quick look at the time command, because as I say, some of you may have used this in the previous assignment, and it's always something good to use because it's very simple. You just put in front of your program and you run it. Sometimes I even do when I submit a job to the cluster, I just, instead of just calling my program, I just put time in front just to have a double check, because the scheduler usually reports the time that the program takes to run, but if you want to double check that, is something you can easily do. It's very simple, it's very cheap to do. So one thing to bear in mind is that when you're running an application in serial, meaning that it's not parallelized, time will report something like real time, user time, and system time. So the real time is what we call usually the wall time. It's the total time that the application or the program took to run. Then what you will see is that the real time is equal to the user time plus the system time. So what happened here is the operating system can differentiate between these two, and basically when it's saying something about system time, is referring to file I/O operations, access to this, access to libraries, anything that is related to file I/O. Of course, all these times, these 2 times, contribute to the total time of the application running. But sometimes it's very useful to take a look at these 2 and see where most of the time is being run. Now, this is in serial, where the case is quite simple because you just have one thread or one application running, no problem there. In parallel, what you really or ideally would like to see is that the user time is equal to the number of processors or number of processes or threads times the real time of the application. And so that's the main idea. One thing that some people do is you can run tests to identify performance regression. So you can run some sort of regression analysis in your performance and getting signs by looking at these times as well. Okay, so this is an example of the top command I showed you just a few minutes ago, htop. But in this case, what this example is showing you is just, as you can see, and you probably have seen this already, the top command is a little bit less verbose in terms of the CPUs. It just gives information about the processes per se. So in this case, there is an application where there are 8 threads running. And one thing that you can see is that this application is using more system time than user time. And if we go back to what we just mentioned before, this may be indicating that the file system or this application is using more file system than anything else. So in that regards, it's not quite efficient. So that's an example of what the kind of diagnostic you can also get from top in combination with time. And again, so these tools are already on the operating system, so they are very easy to use. It's just using the command and it will provide the information for you. So we talk about instrumenting the code, and the TikTok routines, the TikTok calls were an example of this. The approach is quite simple. You just put a tick, a talk, you measure the part of the code, and it just works. The nice thing is that it's tracing, so that's why it's called tracing. It runs every time that you run the code, so it gives you a very detailed information of view of how the code is running. And one of the things is that it can very easily see if any changes that you are doing is improving or degrading the performance of the code. So it's something that is good to try. This is an example of the tick and talk routines. Basically, you need to use one of the standard get time of the functions from the standard library of C. In this case, it's just doing some math to get the talk. So you start by getting the time of the day at the time that you actually activate tick, and then you get that again when you activate talk, and then you just do a little bit of math there to compute the difference, and it will return the difference between the tick and talk. So again, very simple idea, very simple approach, quite efficient in terms of informing about changes. So this is the way you will use it. Again, you will need to include the time.h header file in order to be able to get the time of the day. And this is just a couple of examples where you will use the tick and talk in order to measure different parts. So you can put it as many times as you want. You just keep track of whatever is the variable that you are using for each of the TikToks. And then you measure as many times as you want at different parts of the code. So it's a very nice and an easy way to just follow around. Of course, the price that you pay here is that there is extra code floating around in your main code, in your original code. But again, there is no free lunch here. This provides a lot of detailed information about the performance of each of the parts that you decide to measure within the code. Okay. So let's take an example, a probably very well-known example by now. So this is a matrix vector multiplication. And the code I'm going to show you is doing it from scratch. And of course, you will never do this, right? And actually, because I hope that the ones that are following the lecture can tell me. So because I leave it to be completed in the chat, why you will never do this from scratch. And you can see what I'm doing. So I'm basically just having two for loops nested and doing the matrix vector multiplication. So what I'm going to do here is, this is a complete code, and we're going to see where this code is spending most of the time by just implementing the TikTok that we just saw before, implementing these timers within the code. So this is the initialization of the data. So I'm going to just initialize the vector and then take the transpose, or actually, if similar to what you saw in BLAST, if there is a transpose, compute the transpose, else do something else. And this is the actual multiplication. So I'm going to do again another tick here. So I'm going to have a TikTok for the initialization and then a TikTok for the actual computation. So I'm saying if the transpose, and this has OpenMP session, so this is a parallelized way of doing the multiplication. I think Ramsey shows something similar with the SASP routine. If it is not transposed, do the other way around. So it's just reverting the way that you just loop over the indices. In any case, this is the matrix vector multiplication. Nothing surprising here, so just take element by element of the matrix, multiply by the vector. And of course, the reason why you will never do this is because we have specialized libraries that can do this for you in a more efficient way and specialized way. In any case, take it just as an example for seeing how we instrument the code to measure the different parts, the initialization of the data and the calculation itself. Okay, so in this case, this application takes a flag, so where you can specify the size of the matrix. So in this case, 2500 by 2500. So when we run this, and the part that I'm not showing you here is the input and output. So this program also has the capability of saving as ASCII or as binary. So that may ring a bell from our file.io lecture some time ago. And so we are going to instrument each of the parts: initialization, computation or multiplication, and the output. So when we do that, when we run our code, and this again will modify the structure, will modify the content of your code, but we're talking about instrumenting 3 sections, something around 12 lines. So it's nothing crazy, something that is quite doable. And when you run in this way, what you can see from the total timings, so is that most of the time is spent on the I/O. Right? And again, this is not an optimized code in the sense that it's not using any of the specialized libraries like BLAST or something like that. But again, that gives you a very clear hint of where most of the time is being spent. We could have timed this with time, but time will give you the whole overview, like the whole time that the code is being run. But the way of doing this instrumentation by sections give you a very clear idea of where most of the time is being spent in the code. So that's why it's very useful to do this kind of analysis. So the code spent most of the time doing I/O is kind of not surprising, as I was saying. If you recall our file.io lecture a few weeks ago now, the code was by default doing the output in ASCII. So ASCII we know is not efficient because, well, first of all, we were dealing with double numbers, and there is a conversion that has to be done for writing into the characters represented in the ASCII format. So that's one thing. And then ASCII is very heavy comparing to binary to a binary option. So this code has a binary option, and I'm just listing here both how you will do the writing in ASCII, how you will do it in binary. Again, you have seen this. By the way, this is the C way of doing the binary, not the C++ way. It shouldn't matter in any case. But just by looking, it's even shorter doing it in plain binary than in ASCII. So that's another thing to bear in mind, is less code. But in any case, we are after measuring the performance of the code with respect to the time spent for writing the data to the file. And when we do that, so I have my old timings here, and the new run with the binary flag, what you can see is that it's basically 30 something times faster. So it improved a lot the performance, and now something else that you can notice is that the timings are more or less of the same order. There are maybe one order of difference between the calculation and the initialization. Of course, this is done just once, and the file I/O. In addition to that, not only saving in ASCII is slow, but also look at the file sizes of the files. Is also less than 3 times smaller, the binary output. So again, this is a preach for using binary whenever you can, but also an example of how you can get insights or evidence in this case that actually file I/O is still being the slowest part in the program itself, by just instrumenting the different parts, the different regions in the code. Okay. Looks like the chat is quiet, so no questions so far. So this is kind of a recap of our whole lecture on file I/O. Whenever you can, use always binary formats for I/O. There is no conversion needed, so you reduce the CPU utilization. Usually generates smaller files. There is no precision loss, we didn't talk about this, and even more advantageous is to use standard formats like NextCDF that you guys already tried. The other thing that is worth to mention, especially that now we're in the parallel part of the code, of the course, is that in particular with parallel file system, having a lot of small files is something that is no good. So whenever it's possible, try to bundle things and create a bigger, less number of files. So we have talked about instrumenting codes. We saw a couple of examples using these TikTok routines. Let's look at a different approach, which is the sampling. So sampling allows you to get finer grained information about where the time is being spent. The thing is that if you have a very complex code or very long code, you cannot instrument every single line. So how we can do that? How we can basically don't change so much the structure of the code by decorating with TikTok routines everywhere? Well, the approach is then sampling. So the idea here is that while the code is running, you will be sampled where the code is being executed, in which line, in which function the code is being executed. Now, the thing is, if you do this many times while the code is running, then you may get an idea where you can basically recover the picture of where the time was spent during the execution of the code. The good news is that compilers have tools for sampling the execution paths, meaning these function stacks that we have talked while looking at the debuggers. The compilers can help you and will help you, will provide you information of where the pointer of the instruction being executed is by tracking that. So so let's say that, and this is the same program as before. In the case of sampling, we won't have any instrumentation. We can leave the instrumentation there. There is no problem there. It's very unlikely that the 12 lines that we added of instrumentation will be sampled during the execution of the program. But if they are sampled, it can be just a statistical noise. By the way, this is a method based on statistics. So of course, in any statistical analysis or approach that you may take, as many samples you have, or as larger number of samples you have, the more accurate, the more robust will be your result. So let's say that we have the program running for a few seconds. So every so often, like around, I think the default is 100 milliseconds or so, the execution where the program is being executed is going to be recorded. And if you have a good number of samples, then you can reconstruct this. Of course, the caveat is, as I was mentioning, the program has to run for long enough so the number of samples can be cranked up. So in this case, if we do a sampling of our matrix vector multiplication example, then you may say, oh, it was the first instance looking at line 7, 18, 2, 23, 9, and so on. So the collection of all the instructions that were executed are sampled at that time. So what are the advantages then of the sampling? Well, it has very low overhead. It basically doesn't interfere with the timing of execution. That's very important. The instrumentation, if you do properly, is supposed it wouldn't, but in principle, it's more code. So if you are instrumenting a routine within a for loop that is executed 1 million times, then that time that is being spent during the timing itself will start to add up to that, right? The sampling is different in that regards. It has very low overhead. The other advantage is it does not require any extra instrumentation, so your code remains as it is. The disadvantage is that it don't tell us why the code was there. So it was there at that point. It may have been there because it hit a if statement where it was true or not, or different conditions. So that's one of the disadvantages. The other is the statistical side of things, so that you need to have a long enough run in order to have a good sample size. But other than that, it's supposed to be okay. And usually you will profile things when you are concerned about the timing that the code is running. So having long runs shouldn't be a problem for profiling. So how we do this? Well, I was telling you the compilers will help with this. So what we need to add, and I have here the two flavors of the compilers, either the Intel compiler or the new compiler as we have been using. We need to add a couple of new flags. One we already know because we use it for debugging, is to activate the debugging symbols. It's optional as usual, but as usual is more enlightening because it can give you the actual name of the functions or the variables involved. So unless you want to deal with hexadecimal coding, I would recommend to do that. And then PHY is the one that turns on the profiling per se. Now, we need to compile the application. So this is the application I was showing you before. We need to compile the application with the actual flags. By the way, there was a very interesting discussion. So I'm open a parenthesis here. There was a lot of use of the forum as we were expecting because of moving things online. And there were a lot of interesting discussion, and actually I ended up recommending to some of you asking questions to look at that. So it's really good that you guys are very active in the forum, so that's great. So let's try to keep it like that. There was the reason why this I was talking about that is because some of you were talking about these optimization flags. We are going to be talking about the optimization flags on next class, by the way. But in this case, it's good that, so usually when you debug, so this is a difference when debugging, you try to turn off the optimization flags so you can try to follow more or less the way that we wrote the code, because when we do some optimizations, the compiler takes some freedoms and rearrange the instructions so that it can be executed more in a faster way, depending on the level of optimization, of course. But in this case, we want to keep the level of optimizations that we would like to use for running the code, so we can actually profile what is our production run, for saying somehow. So this is how we will compile the code. Then we run the code as we will usually do. The code will run, it will have some output. If we have our instrumentation part, still is going to tell us about the timing. But the main difference is after the code has run and we look at the files, there is a new file here called shimon.out. So this is the file where it contains the information about the samples collected during the execution of the program. Okay. So again, this is what we are going to be looking at to see where the program spends most of the time running. So we need a tool for looking into that, and the tool that we are going to use, again, this is available in most operating systems, and I believe is installed when you install the compilers, is shiprof. So what we want is shiprof, the name of the executable, and notice that because I compiled with the PG flags, I rename it to MVM matrix vector multiplication dash profile, and then the shimon.out file associated with that. So when you just run shiprof executable and then shimon.out, what basically it gives you is a flat profile. So basically it tells you the data in which functions the time was being spent. So it says, okay, you main spend, and this is in percentage, so 100% of the time, of course, because main is the function that has everything, and then you have cumulative seconds, cell seconds, calls, and so on. And in this case, because the toy problem is not so enlightening, but you can see how each of the functions being called, even the basic functions or the low-level functions, are reported here. Okay. Now there is a way. So again, because this is a toy problem, it's a small problem, sort of. It's not too enlightening, but there is a way to get more information or get the information associated with the actual lines that are being executed. So if you run shiprof -- line, and then we py with more to see the different reports, what you will see now is line by line. So here this is the line where this instruction was executed, line by line, where the code spent most of the time. By the way, another parenthesis here, this is another good reason why having a modular code is something that will benefit as well here, because having a monolithic code can give you this kind of very verbose and long output where you don't really know in which function, in which module you are spending most of the time. You have to go and look into your code. By having a modular code, this information will be way cleaner, aggregated in the different modules where you are spending the time. So what can we conclude about this? Well, if we look at the flat profile again and we look at the lines in this particular code, basically we see something that we saw with the instrumentation part before. Most of the time is being spent in line 82, where it is basically one of the for loops where the multiplication happens, and then the other is in line 113, where it's basically the output. So again, no surprises here, but another way to get kind of the same idea, the same understanding of what the code is doing, but with a different approach. So we could have taken, for instance, just the sampling approach without tick-tocking our code, and more or less end with the same conclusion. So multiplication, of course, the computation, and then the output. So just a quick summary about shiprof. It's very easy to use. You can actually script in your submission scripts. It has very low overhead. And again, I'm just showing you the plain output, but there are graphical interfaces that make this thing kind of look very, very nice, very appealing, not so plain like the just plain output of shiprof. So we're going to keep talking about profiling, but we are going to change the metric now. So we have talked about the time as a possible metric, but what about memory? What about memory utilization? What about if for application or problem is memory bound and not so much compute bound, or what about if we are limited by the memory of the architecture where we are running? So that's why we may want to take a look at the profiling by memory. So there is another tool. This is an open source tool again. This one is not by default, so you probably need to install it. It's already available in the Teach cluster. It's called Valgrind. And actually Valgrind is a set of tools mostly aimed to analyze memory issues. So we have, within Valgrind, we have something called Massive, which is a memory heap profiler. So that allows you to see how the heap memory behaves. And then we have Cache Grind, which is a cache profiler. And the way you run it is you run Valgrind, you select the tool that you want to run, Massive or Cache Grind, and then you run your code. And depending again what you prefer, there are a kind of terminal tool that allow you to digest that, or there is a GUI. It's called Cache Grind. For instance, this one a little bit old, but it still has a GUI to interpret the results. So let's take a look at just the output of MSprint. That's the interpreter in the terminal for Valgrind. I have to warn you, it's very verbose. It has a lot of information. It tells you the tiny milliseconds, the iteration, for instance, and then the total memory use, the heap, if there is extra heap, and the stack. Now, the interesting thing, this is just part of the output. The interesting thing that Valgrind can do for you, it can tell you about memory leaks. And again, this is quite interesting because sometimes we forget to deallocate some memory. This happens especially if we are allocating dynamically or statically, but it doesn't matter. If we just forget to deallocate, Valgrind keep track of that, and it can tell you if there is some missing deallocation happening. So if the code is leaking, that's the jargon for when we forget to deallocate the memory. Now, related to that, and why this is important, is I think we talked about this a little bit some time ago again, is something referred to as cache thrashing. So what happens if we have a vector or an array in main memory and we need to perform some computation? So one thing to remind us all is that main memory is usually big with respect to the memory that you can allocate close to the CPU, where that's what we call the cache, but it's also slow. So the cache is smaller than the big memory, but it's way faster. So what happens is that the cache saves one line of the memory that we access. So if it happens that we need to access an array that is linearly allocated in memory, and then we access each for doing a computation, then if we are accessing in order, then when we need the next element of the array, it will be right there in the cache. So we don't need to go back to the big memory. The program doesn't need to go back to the big memory. It's right there waiting for whatever operation you want to do. So that's way faster. Now, if the allocation is such that instead of having in contiguous sectors, we have dispersed, or our computation is not accessing the contiguous element, but the next one, then we need to basically trash whatever is the content for processing the second element, and then grab another piece of the of the allocation in the big memory, bring it back, and so on. So this can result, this cache thrashing thing can result in a slowdown of your code up to 10 times. So in really bad situations, this can really affect your performance. Nothing else than just by not having the memory allocated in the right order, or not accessing the memory in the right order. And I'll show you an example in a second of what I meant with this. So this is our matrix vector multiplication program again, just the snippet where we are actually doing the computation. So in this case, you see that the for loop is done in the latest index in the matrix, while in this case it's done in the first one. So just by reverting this for loop, the I here is first, the j is after, so that's the second index of the matrix. The j here is first, the I is after. So just by changing that, because the way that C stores the data in memory, that may affect the performance of the code. And again, that's something you can see with Python. Okay. And the other thing is that this KDE, so this is an old desktop tool for Linux, is available for most of the operating systems as well. So that's something to take a look. Okay. So this is how it looks like. So in the teach cluster, if you want to use Vagrant, you just do module.vagrant, and you just run Vagrant with the change grind tool, the application, any parameters that you may use, and that's it. This is how the KDE looks like. If you have the chance, I don't believe we have that installed in the system, but you can try to download it and use it in your own computers if you want. So once the cache thrashing is fixed, now assuming that we cannot improve I/O anymore, so our bottleneck is the initialization. And as I was saying at the beginning, there is no much worth spending time in looking into something that is just of the order of the computation and is done only once. So this is as far as we can go with this particular code or this particular example. So let me quickly talk about other profiling tools. Some of them are open, some of them are you have to pay for them. Escalaska is a good one. So there are some HPC toolkits. DAO is a very interesting one. I believe these ones are open source. I'm not sure about Escalaska. The one I wanted to mention as well, in particular, because we have it available on the cluster, at least part of it, is the Alinea map tool, or now it's called Forge. It's, by the way, the same tool that you have with DDT, the debugger. If you are using the Intel compilers, it's worth spending some time looking at BTune. People using BTune and again using the Intel compilers and using specialized architectures speak wonderful things about it, because it can really help improving the performance. So again, if you are developing your own app using Intel compilers and using the specific architecture where the registers can inform the compiler about what type of things are doing, then that's a tool worth spending some time looking at. If you are developing in OX, Xcode is supposed to have some tools similar to that. And of course, if you are doing some CUDA or CPU programming, NVIDIA Profiler is kind of the equivalent to the profiler that we saw today. So NVProf is similar to SheetProf on that regards. And again, that's a new hardware, because memory transactions there between the host device and the CPU is one of the bottlenecks usually. So these profilers can give you more insights about that. So again, having the proper tool depending on the architecture is something interesting. As you can see, my cat is very interested in these tools, so I apologize for that. So this is part of the Intel tools. The Intel Parallel Studio XE is where you will find BTunes and so on. I don't believe we have this available on the cluster. I do think though that if you are working in your projects, Intel may have some free version for students, something to explore again. But this one is the one that you guys can use if you want to explore applications in the cluster. This one you have to pay, but we have licenses for it, so it's a really nice tool. It's a very complete tool, and in addition to that, it not only has the profiler, it has the debugger, and this debugger can also debug MPI applications. It can debug CUDA applications as well. So it's a very powerful debugger. This company is specialized in this kind of tool, so they really have a really good product here. There is another tool which I was discussing with Francis yesterday. We don't think this one is available on the cluster, but it's very nice. I will show you the type of reports this tool will generate for you. It's called performance reports. I'm not certain why it's not part of the module we have, but it is not right now. So, but in any case, again, if you have the chance, it's worth taking a look at it. And then map is the one that will provide you the profiling options here. So this is what performance report will generate for you. After you run application, it will collect the statistics about the application running. For instance, it will grab the statistics about the actual node, the number of physical and logical cores. So this is hyper-threading enabled, the memory, how many processes were running, the type of machine, how long it ran, and so on. So what is really nice of performance reports is that it can very quickly give you a sense of your application, of what dominates in your application. If it is computation, if it is communication, that's the MPI part, or if it is I/O. Okay, so and it has this kind of triangular representation where you can see here computation is being the dominated part in this application. So this is a very nice fine-tuned application, as you can see. The other thing that you can do with map is you can trace now the thread activity. So you can see the MPI calls, sends, and receive. Again, this may be quite useful in particular for this week's assignment. If you're struggling with balancing your MPI calls or seeing how they perform, this may be a nice tool to explore. Or just if you are curious about how the balance goes with the communication and the computation, this is a nice tool to take a look at. And I think that's mostly what I have for today. Just a quick summary of profiling. So there are two main approaches: tracing and sampling. So tracing is basically decorating new parts of or pieces of your code with new instructions in order to take the times. While sampling is just a more passive way, in the sense that you don't need to do much other than compile with the proper flags, and then post-process the output generated while the application ran. So that's another advantage of sampling. You can just have a run of your application and then post-process the output. So for instance, if you are doing one of these rack allocations where you request resources, we usually ask you to provide a scaling analysis of your code. So if you are running one of your production runs, let's say, you can at the same time do the sampling and then do the projection of the scaling analysis. You can put your own timers in the code, as we saw today, just to determine the time that each of the important sections in the code are using. And if you change something, get an idea how it affects that particular part of the code. SheProf is very easy to use, excellent tool at finding where the time is being spent. Again, something to bear in mind is be aware of where the expensive parts of the code are, and spend your time programming accordingly. So if initialization is something that, you know, takes 1-2% of the total time of the code and it's only done once in the code, again, maybe it's not worth spending the time improving that. Bikeline is an open source tool really good at memory profiling. Alinea Map is a great tool, and again, usually you have to pay for it. In this case, you can use it for free because it's available in the cluster. And something else I should mention about the Alinea tools, the Force tools, is that there is a way to use the graphic user interface in what is called a client-server mode. So usually when you run things graphically in the cluster, you need to tunnel with a specific flag for getting the graphic back to your computer. That's usually very slow, and is depending on your connection, can be like really bad. But when you have this client-server mode, basically you have an application running in your laptop or your computer at home, and then the server running on the cluster, and they only communicate the information they need to basically display the information for you. So usually it's faster, more responsive So it's something that is really nice to try. I think the last assignment for the course is going to be about profiling things, and we may want you to explore that tool. So you may need to read some documentation on how to use this client server thing, but that's something that we're still cooking. So we probably can tell you more about this next class or during the office hours. By the way, something I forget to mention, I think I mentioned the time for the office hours, but we have been hosting the office hours online using Quarkus, and I think it has worked pretty well. At least the experience in our side was very positive. Again, if you have something to say or would like to share your experience about that as well, please don't forget to complete the course evaluation. And I think that's all what I have for today. And as Francis is pointing out, the Alinea tools are now called ARM tools because that company bought the Alinea tools. So there you go. And yes, that's all what I have to say. Office hours are going to be instead of today because we just posted the assignment yesterday, so you probably didn't have enough time to look at the assignments. The assignment yet, so it's going to be tomorrow from 2 to 3, and then Friday I believe at 11 in the morning. But again, if you have questions, you can always post in the forum and write to us at courses@signet.utero.ca. Okay, I will see you again on Thursday.